This is lecture 5, and in this lecture we'll be talking about light and the origins of quantum theory. Now, I said that we as chemists care about matter and only really about energy when it's interacting with matter. So why are we going to spend a whole lecture talking about light? Well, it's because we're going to need to understand certain properties of light if we're going to understand the atom better. So far we've talked about the atom and how there's this really tiny nucleus with all the positive charge in it. But we haven't really spent much time at all talking about electrons. Now, how are electrons filling that big space around the nucleus? What do electrons act like? What are they? How do they behave? And to understand that, we're first going to need to understand light. Now, in the 1800s, by the late 1800s, there were certain things that were pretty well understood about light, and specifically that it could be described as a wave. And physicists had worked out that light had two components. It had an electric component and a magnetic component. And so light moved through space like a wave with an oscillating electric field. You could think of that as oscillating up and down, and then an oscillating magnetic field that would oscillate side to side. And so you have these two waves going at the same time, propagating through space. So as this light is traveling through space, it has this kind of up and down rhythmic motion to it, and it's got that going on in 2 dimensions. And so this is why light is described as electromagnetic radiation, because it has these two waves, the electric and the magnetic waves. Now, since we're going to be talking about waves, I need to give you the jargon for talking about waves, or the specific vocabulary you're going to need. So right here I have a diagram of a wave. This could be drawn with as a sine wave or a cosine wave, just something that goes up and down regularly. Now the wave at the top has what we call the peak or the crest. So that's the highest point on the wave. It also has a trough or a bottom. We generally call it a trough. The trough is the lowest point of the wave. We also then want to talk about the height or amplitude of the wave. Now you'll notice the amplitude is not the distance from the bottom to the top. It's half that distance. So it's the distance from the middle to the top, or from the middle to the bottom. Since waves are symmetric, the distance from the middle to the top is always the same as the different distance from the middle to the bottom. I also want to introduce the idea of a node. A node is where this wave passes through a 0 point. Now what that means is that when you're above this 0 point, your wave has a positive value, and when it's below it, it's a negative value. And this, of course, isn't necessarily talking about positive and negative in terms of charge. This is just describing the numerical value of the wave. And these points where it's 0 will become more important as we go on. There's 2 more concepts I want to introduce you to about the wave. The first is wavelength. We usually describe wavelength with the Greek letter lambda. And one wavelength is the distance from the bottom of one trough to the bottom of the other, or from the top of one peak to the top of the other. It's the smallest amount of the wave that if you cut it and then copied and pasted it, you would get just a continuous wave. So the wavelength then is that distance, and we generally describe it in meters. The last concept we're going to talk about with waves is frequency. Frequency is most often described with the Greek symbol nu. Now in physics, they use an F for frequency. We use nu in chemistry, even though the nu looks like a V. It's fun. It's interesting. We'll go with interesting over fun. So frequency, though, is a measure of how many wavelengths pass a specific point within a given amount of time. So you can imagine if you have 2 waves right here that are going at the same speed, the wave with the shorter wavelength more of those wavelengths can pass a point all at once, right? So you can, just in this box, you can have 1, 2, 3, 4, 5, 6, 7, 8, 9 peaks, or roughly 8 wavelengths. And if you have a lower frequency, or you have longer wavelengths, right? Then in this box, you only have 1, 2, 3, 4, 5 peaks, or about 4 wavelengths of light. So with the high frequency light, with the low wavelength, you're going to have more wavelengths passing at a given time. And frequency is measured in units of hertz. So a hertz is equal to 1 per second. So, or in other words, an inverse second. So 1 over a second. We refer to those as per seconds. And what I've already talked about a little is this relationship between wavelength and frequency. As wavelength goes up, frequency goes down. So for this high frequency wave, you have short wavelengths. For this low frequency wave, you have long wavelengths, or larger wavelengths. So let's see how you're dealing with that information with an iCLICKER quiz. So go ahead and read through this problem. It's describing, or it's about these 2 waves, wave number 1 and number 2. Try and figure out which statement is true about these 2 waves. Go ahead and pause the video, and then we can go over this. All right, well, let's first just look at these waves and figure out some properties of them. So we can see that number 1 is higher or taller, so it has a greater amplitude than number 2. We also see that the wavelength on number 1 is longer than the wavelength on number 2. Since the wavelength is longer on number 1, that means that the frequency must be longer on number 2. So this one has a lower frequency than this. So now let's take that information and go through the statements A, B, C, D, and E to just eliminate some and get to the right answer. All right, so we know that number 1 has a greater amplitude than number 2. So number 2 having a smaller amplitude is true. So A fits that, C and D all fit that, but now we've eliminated B and E. We know that the wavelength on number 1 is longer than the wavelength on number 2. So number 2 has a smaller amplitude wavelength, that fits. Number 2 has a smaller amplitude and wavelength, that fits. Number 2 has a smaller amplitude but greater wavelength. Well, that doesn't fit, so we can eliminate D. And now we just have to decide between A and C. In A, it says number 2 has smaller amplitude, wavelength, and frequency than number 1. That's actually an impossible statement. You can't have both a lower frequency and wavelength. You have to have one or the other. So A can't be true. So it's C. Number 2 has a smaller amplitude and wavelength, but greater frequency than number 1. And actually for light, the relationship between wavelength and frequency is fixed. And it's fixed by the speed of light. And then what I mean by that is that the speed of light is actually equal to the wavelength of light times the frequency. So as you get to longer wavelengths of light, the frequency has to decrease, or else this ratio of wavelength times frequency wouldn't be a constant, and C wouldn't be a constant value. So if one of these goes up, the other has to go down in order for the speed of light to stay constant. Now the speed of light is equal to 2.99792458 times 10 to the 8th meters per second. Now that is an actual measured value, and in physics they use that value all the time, and in more advanced chemistry classes you might use that value. In this class we don't need to use that many digits, so oftentimes we'll just use a shorthand and just say that the speed of light is about 3 times 10 to the 8th meters per second. And you can see that that's actually pretty close to the true value. But just recognize that as we go on, that is an approximate value, and we do know it a lot better than that. It's too cumbersome to use the big number all the time. But because the speed of light is proportional to wavelength and frequency are inversely proportional, We can then take that information and use it to describe the entire electromagnetic spectrum. The electromagnetic spectrum just describes light of different wavelengths or different frequencies, and dividing those wavelengths or frequencies into different regions. And so what you can see, hopefully, if you have good glasses on, is that as the frequency of light decreases here, the wavelength increases. And in our really long wavelength region of about a tenth of a meter or about 10 centimeters on up to hundreds and thousands of meters long, this is our radio waves. So radio waves actually consist of really long wavelengths of light. And the length of that depends on whether you're using AM or FM or those secret military channels. But there's your radio waves. After radio waves come your microwaves, and this goes from about 10 centimeters on down to millimeters and sub-millimeter range. At that point, we shift into the infrared region. So infrared covers a broad range of wavelengths as well. Beyond infrared is the very narrow visible range. And so the visible range is between about 400 nanometers and about 700 or 750 nanometers. And the exact cutoff actually depends on the individual and on the specific structure of your rods and cones in your eyeballs. At lower wavelengths beyond the visible is the ultraviolet. After ultraviolet is X-rays, and below X-rays is gamma rays. So with this, I do need you to memorize this entire spectrum. You don't necessarily need to memorize the frequencies or wavelengths that correspond to each region, but you need to memorize the order of these different regions. You need to know that gamma rays are super short wavelengths, super high frequencies. Radio waves are super long wavelengths, super low frequencies. And you do need to memorize the order of the visible spectrum, which goes red, orange, yellow, green, blue, indigo, violet. Right? There's no purple in there. And so the acronym that's very helpful for memorizing this is Roy G. Biv. Doesn't sound like anything or mean anything, but if you can remember Roy G. Biv, Roy G. Biv, then you can even write that out on your scratch paper while you're taking the test, and then you can remember, oh, red, orange, yellow, green, blue, indigo, violet. Okay, so go ahead and memorize all of that. Now let's try and do some calculations with this equation. So C equals lambda nu, the speed of light equation. And I'll give you some example problems. So let's say let's talk about medical x-rays. They can have frequencies of about 1.4 times 10 to the 19th hertz. And that depends a little on your instrument and how much power it's getting. But let's figure out what the wavelength of light coming off of that is. So to do that, you're going to have to take this equation right here, and you're going to have to solve it in terms of wavelength. So then wavelength will be equal to c, the speed of light, divided by the frequency of light. So then we can just take 3 times 10 to the 8th meters per second, the speed of light. And yes, you do need to memorize that number as well. We'll take that divided by the frequency. And then you'll notice we have per seconds on the bottom. We have per seconds on the top. So those per seconds will cancel out. We'll get an answer in terms of meters. And that'll be 2.1 times 10 to the negative 11th meters, or 21 picometers. So pretty short. Now let's put that in context. And there was a daughter of a professor in our department who, when she was a little girl, broke her arm. And they went to the doctor, the medical doctor. So I'm an academic doctor, or the original doctor. But they took the daughter to a medical doctor and had the doctor take an x-ray of the fracture. And so we don't really care about what the bone looked like, but what we're going to worry about is that the little girl's arm was about 4 centimeters thick. So that's only about 1.5 inches thick. Oh, that poor little girl, poor little arm. But what we want to figure out now is how many x-rays, or how many wavelengths of the x-ray could fit in that arm simultaneously. So what we're going to do is we're going to just take this 4 centimeters and convert it into picometers. So 4 centimeters per arm times 1 meter per 100 centimeters. So now we've turned it into meters. And then we can go from meters to picometers because it's 1 times 10 to the 12th picometers per meter. So now we've gone from centimeters to arm or per arm to picometers per arm. And then we can multiply that by the wavelength, or sorry, divide by the wavelength of the X-ray. So it's 21 picometers divided or per 1 wavelength. We work that out and we get 1.9 times 10 to the 9th wavelengths per arm. Or in other words, there's about 1.9 billion X-rays crossing her arm, which is gives you good context. So these are pretty tiny. Compare that to microwaves that can be as long as your house or your apartment, right? Very different lengths. Oh, sorry, I think I said microwaves there. I meant radio waves, which can be as long as your house or apartment. Let me give you a calculation, and I want you to work this one out on your own. So a cell phone operates at a frequency of 1.9 gigahertz. What is the wavelength emitted? So you need to think about what equation you need to use here, and then you need to solve the problem. So go ahead and pause the video and do that. All right, so I'm not going to go through all the steps of the math like I did on the previous page, but you should have gotten 16 centimeters, right? You should have taken C, set it equal to lambda nu, and then solved for lambda, etc. All right, so a wavelength of the energy or the photon being emitted from your cell phone is 16 centimeters. So how many wavelengths do you think can fit inside the human head? Well, as it turns out, totally coincidentally, the human head on average is about 14 to 16 centimeters wide. So it's about the width of the signal coming off of your cell phone. This is pretty fun information. All right, so now we know quite a bit about light. And all that was mostly figured out before 1900. And in 1900, light had been described really well by Neil Maxwell, who was actually an Irish physicist. And so he described light as a wave, and the motion of objects had largely been worked out by Isaac Newton. And so most physicists really thought that they had figured just about everything out. There were just 3 big unsolved problems that everyone was still focused on, but most physicists felt that within a couple years we were going to figure those out too, and then we would just completely understand the universe. And those problems were the problem of blackbody radiation, the photoelectric effect, and the line spectra of atoms and molecules. And we're actually going to spend the rest of this lecture talking about these first 2 problems, and then we'll spend next lecture talking about this last problem. And what you'll discover is that as we think through these problems and find the solutions are actually going to completely reshape the way we think about matter and energy. It's really going to throw our current understanding out the window. And I actually won't be able to give you all of that, but I'll be able to give you quite a bit here. All right, so let's start with the idea of black body radiation and why it's important to us. So black body radiation is the light that's emitted by a black body. And what a black body is something that at room temperature looks black. Now that doesn't actually mean it's the color black. Really what it means is it's not glowing. So for example, silver metal is not glowing, so it's a black body. Inert gases are not glowing, so they are black body, even though many of them are transparent and colorless, so you can't actually even see them. But at high temperatures, black bodies emit light. They emit this radiation in the form of electromagnetic radiation. And what physicists knew about black body radiation was that as the temperature increased, so you can see on this plot right here, I have wavelength on the x-axis, and I have the intensity of the light on the y-axis. And as the temperature increased, the intensity of the light would also increase in these black bodies. That's still true today. But also what would occur is the peak wavelength, so the most intense wavelength, would also shift as you increase the temperatures. So here at the bottom I have a material at 3000 Kelvin, and 4000, 5000, and 6000. And the point where that peak wavelength is at really controls what color we see with our naked eye. And so as you increase the temperature, you're increasing the intensity, but you're also lowering the wavelength, the max wavelength, or in other words, you're increasing the maximum frequency of that light. And because of this shift, we can actually figure out what's going on in stars to some extent. So what I mean by that is our star is yellow because it's a black body made of hydrogen and helium and some other minor elements that's really hot. And when it's really hot, it has a peak wavelength emission at a yellow light. Sorry, muddled through all that. It has a peak wavelength that corresponds to yellow light. And so this is how astronomers can tell the temperature of different stars. You just look at their color. So red stars are actually colder than blue or green stars. But the problem with black body radiation wasn't the fact that we could measure it. The scientists could actually measure it just fine. The problem was that they couldn't explain it. When they used classical physics to explain it, they got something that looked very different from the measurements. So here in the colored lines, I'm showing measured data at different temperatures. So these are the wavelengths being emitted, and they're different intensities. But when physicists tried to model this using classical physics, you'll notice that they got something that looked very different from reality. And the real problem was that this line just keeps going up forever, and results in what we call the ultraviolet catastrophe. And that term comes from the fact that this model would then say that in the ultraviolet region, these black bodies should be giving off infinite energy, which just isn't true. It's not the way reality works. Additionally, what I didn't mention very clearly before is actually black bodies are emitting electromagnetic radiation even at low temperatures. So many metals that you see lying around are actually emitting electromagnetic radiation all the time. It's just in the infrared, so you can't see it. You can sometimes see it faintly if you're wearing infrared goggles, which is what people used to see with at night. And the reason those work is because different materials give off different amount of this electromagnetic radiation. All right, but big problem, classic physics doesn't match experimentation. So theory and reality are not matching up. So along comes Max Planck, who looks really friendly. So in 1900, Max Planck came along with two new assumptions, and these both violated classical physics. The first assumption that he put forward was, instead of describing energy of light as being proportional to the intensity or how bright the light is, let's instead say that the energy is proportional to the frequency of light. So higher frequencies, you have a lot more wavelengths of light passing through at a given time. Let's say that means there's more energy. And let's also say that matter can't just absorb any amount of energy. It can only absorb specific quanta of energy. So a quanta is a defined amount. So for example, we could say that that matter can absorb one energy or two energies, but it can't absorb 1.5 energies. And amazingly, that's actually the way reality works. So the classical idea was of this continuous line where you could start from the bottom and absorb energy to get to any excited high energy state, right? So if we think of this axis here as energy, if you give this guy some energy, he can move up this line, and now he's got a higher potential energy. But in reality, you can't just go to any energy level. You actually can only absorb specific amounts of energy. And so there you can either be at no energy, at 1 energy, or 2 energies, but you actually can't be at 1.3 energies. And the reason this was so amazing is because in the macroscopic world where we exist, you don't observe this. Those differences in energy are too small for us to notice. But at the atomic or molecular level, they're actually extremely noticeable and extremely important. And so from this are these two assumptions. Max Planck was able to derive this big equation that gave him curves that matched the data perfectly. Now you don't need to know this big equation, but what you do need to know from it is this h nu guy. So Planck then was able to throw out to the world, the scientific world, a new way of describing the energy that was being absorbed by matter. And he said that the energy absorbed by matter was equal to nh nu. Nu, of course, is that frequency of the light being absorbed. H is a new constant that we call Planck's constant, and it's equal to 6.626 times 10 to the negative 34 joule seconds. So you know what a second is. A joule is a measurement of energy, and a joule is equal to kilograms times meter squared divided by second squared. So, we will do some math with that later, but for right now, just understand that a joule is a unit of energy. And so H, Planck's constant, is just a measured value that was developed in order to make this conversion happen so that energy was still looking the same as it had always looked. And then this n right here is what's known as a quantum number. So we can say that the matter absorbed n equals 1, n equals 2, n equals 3 energy, but we can't say n equals 1.5 energies. And so by introducing this first quantum number to the world, Max Planck set off the idea of quantum theory. Now you've heard of the word quantum mechanics probably your whole life, and it's always been associated with the mysterious art of physics, right? But all quantum means is multiple quanta, and all quanta means is a defined amount. So quantum theory and quantum mechanics is just describing how matter and energy work in these defined amounts. We already know that the proton is quantized. You can have 1 proton or 2. The neutron is quantized. So you can have 3 or 4 neutrons. The electron is quantized, right? You can have 5 or 6 electrons, but you can't have 5.5. And this wasn't really well known until about this time when atoms were really taking shape the way we know them to be now. Well, let's see how you're doing with this idea. I'll give you an iCLICKER quiz and ask you which laser emits light with the greatest energy. Is it the red laser, which has wavelengths between 620 and 750 nanometers? And actually a specific laser only has 1 wavelength of light. This is just describing red lasers in general. Is it green lasers that can range from 495 to 570 nanometers? Is it blue lasers? Is it an IR laser? Or does it depend on how intense the lasers are? And you'll need to understand these 2 equations to figure out this problem. Go ahead and pause the video there. Okay, so what we have to do to figure this out is solve for the energy in terms of wavelength, because I'm giving you wavelength here. So the way we're going to do that is we're first going to solve C in terms of frequency, and then, so frequency C will be equal to C over lambda, and then we can plug that in to our energy equation. So energy, which is equal to h nu, is also equal to hc over lambda. Now I'm going to make a special point here then of emphasizing that energy is proportional to 1 over the wavelength. So as the wavelength increases, the energy decreases. So the red laser here has the highest wavelength that I'm giving you, and the IR laser, IR means infrared or beyond red, and infrared has longer wavelengths than visible light. So that goes back to that electromagnetic spectrum that you need to memorize. But then red lasers have longer wavelengths than green lasers. Green lasers have longer wavelengths than blue lasers. It does not depend on how intense the laser is at all. So the answer is blue laser emits light with the greatest energy because it has the shortest wavelength. All right, so that has to deal with black body radiation. Let's move on to the next unsolved problem. So now we've started dealing in quantum mechanics, but we still haven't figured out a solution to this problem. And what the photoelectric effect is that a metal surface, if light is shined on it, that metal surface will actually give up electrons. The electrons will pop off the metal and fly off. But there's this weird thing where you have to have light of a certain frequency in order to get those electrons to bounce off. And if you have light above that frequency, electrons keep flying off, but if you're below that, nothing happens. And the energy that's required for different metals to give off electrons depends on the individual metal. So what scientists saw was that with low frequency light, no electrons came off. No matter how many photons you hit onto this thing, you could have really, really bright light and it did nothing. But if you had dim light at the right frequency, you could pop off an electron. Now you can see that as we're increasing energy now, we're popping this off, right? We're increasing the frequency. But the number of electrons didn't seem to depend, or the number of electrons didn't seem to depend on the frequency at all. The number of electrons ejected increased with the intensity of light. So if you have 3 photons, you get 3 electrons. If you have 1 photon, you get 1 electron. And then the velocity of the electron coming off, or in other words, the kinetic energy of that electron coming off, increased with increasing frequency, as long as you're past that minimum frequency for electrons to pop off the metal. Now, this didn't make total sense until Einstein came along and he took Max Planck's idea of E equals h nu, or E equals nh nu, and he said, you know what? Each of those n's corresponds to an individual photon of light. And he said that, you know, I know we've been talking about light as waves, but, you know, let's also talk about them as particles instead. And so he said, I mean, you can look at this. This looks just like Max Planck's equation, except it doesn't have that n in there. So Max Planck's equation was dealing with the matter being absorbed by the energy. And this equation has to do with the matter, or the energy being given to the matter from the photon's perspective. And so he said the energy of a single photon was equal to Planck's constant times the frequency of that photon. So now we have a particle, a little bead, that has a frequency because it's behaving like a wave. So we get some weird stuff going on here. And he said that what's going on with the metal, with this photoelectric effect, is that each metal has a different work function. Now, the work function is the minimum amount of energy required to get an electron off that metal sheet, right? So you can think of this as like a rocket trying to get off the Earth. If it has a certain escape velocity, it can get out of the atmosphere and escape, all right? We could call that h nu. And so that's the minimum energy, Planck's constant times the minimum frequency for light to escape, or for the electrons to escape. But if we have a photon that comes in with not enough energy, well, we don't escape because we don't get that escape velocity. If your rocket's not fast enough, it's not going to get out of the atmosphere. It's not going to get away from the Earth, right? It's going to be stuck. But let's say your rocket's going really fast, going faster than the escape velocity, which is almost always true. Then you have a little extra velocity. And with these electrons, that extra energy, so if you have a higher frequency photon than what's absolutely necessary, well, then that photon gave you a little bit extra energy, a little more than you needed. And that extra energy is converted into kinetic energy. And that gives the electron more speed to fly away with. So now the kinetic energy of the electron begins to make sense. So remember, kinetic energy is equal to 1/2 of the mass times the velocity squared. And now we know that the kinetic energy of this electron is equal to the energy of the photon minus that work function, or minus that minimum amount of energy needed to escape. So that work function energy is all consumed in escape, and then any extra energy is imparted in terms of velocity or motion. So here we can change this E, we can substitute in the energy of the photon, which we know is equal to h nu, and then we still have this work function, and we know that that's equal to some amount of energy too, and that's equal to h times nu prime, or sorry, nu naught, and nu naught is just that minimum escape frequency of the photon. The minimum energy is described by h nu naught. And so what happens is if you have a metal sheet and you slowly change the frequency of the light shining on it, you have zero energy, zero electrons at low frequencies until you hit this minimum energy, and then all of a sudden electrons start flying off. And as you keep increasing the frequency of the light, the energy of these electrons keep getting faster and faster, hitting you in the face. Then you got to ask, why are you looking at it? Maybe you do this in a safer place. It's a bad joke. It's not very funny, but I enjoyed saying it. All right, let's see how you're doing with this. I'll give you an iCLICKER quiz. In this question, I'm going to ask the work function of gold is 8.17 times 10 to the negative 19th joules. What is the longest wavelength of light that could eject electrons from a gold ring? In other words, what is the minimum amount of energy you have to give to the ring to get one electron off, and what is the wavelength of the light associated with that minimum amount of energy? You'll need these equations right here, and you'll need these two values right here. Go ahead and pause the video and work that out. All right, so what you're going to need to understand is that at this minimum value, where you're just popping the electron off, then you've just given it enough energy to escape the atom or the metal sheet. So you've given it no extra kinetic energy, right? You've just popped it off, and now it's just sitting here. So we'd say the kinetic energy would be equal to 0 in that case. And then we just need to deal with this work function. And in here, since we're looking for wavelength, and we don't see wavelength in here, we're going to have to figure out how to put it in there. So we're going to do that by making the substitution that nu is equal to c over lambda. So then we can put c over lambda in this equation, solve for lambda. I'm not going to go through all that math on this slide because we've kind of done similar math on previous slides. But if you follow that through, you should have found that the wavelength is 243 nanometers. And that's the minimum amount, or the minimum amount of energy required to pop off an electron. So that's the longest wavelength. So something you got to remember here, right, is if you go into any longer wavelengths, you've gone to lower energies, you're not going to have enough energy to pull that electron. All right, but we've given two different ideas here that some physicists really struggle with. We've given the classic idea of light as a wave and the quantum mechanics idea of light as a particle or a photon. But actually in quantum mechanics, we still think of light as a wave. And really, it just depends on which situation we're in, whether we need to talk about a particle as a wave, or as a photon as a wave or a particle. And so this idea of wave-particle duality begins to emerge. And some people actually have a really hard time with this. But I'm going to present it to you like this. These ideas are just models. They're just us taking things we already understand, trying to apply them to something new to make that new thing more understandable. And so historically, we, as scientists at least, have always thought about particles and waves separately. But in the more modern world, we don't think of them as separately. And in fact, we think of everything as both particle and wave. Everything has wavelengths. Electrons have wavelengths. Protons have wavelengths. Even you have a wavelength. Your wavelength is actually extremely small. And if you go into quantum mechanics, you can calculate your own wavelength and all that. But the idea here is we've actually uncovered a new reality of existence and matter, that everything, even though it all appears as a particle, actually has wave-like properties as well. And so when we're trying to solve a problem, we think of things as either a wave or a particle, depending on which is more useful for solving that problem. Craziness with science. All right, let me know if you have any questions or problems with that. I'll be happy to help you out.